atomic masses or atomic weights. A single atom of carbon-12 is assigned a mass of 12.00 atomic mass units, AMUs. Carbon-12 is our reference isotope. So 1 AMU is equal to 1/12 the mass of a carbon-12 atom. Now the masses of individual atoms are usually expressed in AMUs. It's just a really small unit for measuring individual atoms. The atomic mass of an element is the weighted average of the masses of its isotopes in their naturally occurring abundances. We can get isotopic abundances and the masses of isotopes from what are called mass spectrometers. Here's a mass spectrometer, example of kind of the inner workings of the mass spectrometer. We take whatever gas we're interested in determining, and it goes in this inlet, and it's immediately hit with high energy electrons. When this gas is hit by high energy electrons, electrons are ejected from the gas, and that creates positively charged ions. So over here, we have positive ions. And they're going to be deflected according to their charge to mass ratios. Well, they're all positive, so they're basically deflected by their masses. And you'll see that in this case, there's actually 3 different deflections according basically to their mass. So here is just a summary of what's happening in a mass spectrometer. Again, it determines the isotopic abundances. It will also determine the atomic masses of the different isotopes. Neon occurs in nature as 3 isotopes: neon 20, neon 21, neon 22. And what you'll get from a mass spectrometer is a readout that kind of looks like this. It'll show you the abundance of each isotope along with their masses. And you'll notice that in this particular readout, neon 20 has an abundance of 90.9%. Neon 21 is like 0.26%. It's really not there in much abundance at all. And then neon 22 has an abundance of 8.82%. A mass spectrometer can also be used to determine the atomic masses. So we can get the abundances from the readout. We can also determine the atomic masses of isotopes. So let's say, for example, I want to determine the atomic mass of neon 20. Well, I would, first of all, I would apply a carefully measured fixed voltage to a sample of carbon-12 because carbon-12 is our reference isotope. And I would feed carbon-12 into the mass spec. And I would measure the magnetic field strength that causes the carbon-12 ions to arrive at a specific point A. Then I would feed a sample of neon into the mass spec with the same voltage, same magnetic field strength, and then increase it until the beam of the heavier ions falls at point A. So let me give you kind of an example of some data you would get. So if I want to determine the mass of neon 20, I would kind of compare this to my reference, which is carbon-12, because carbon-12 has a mass of exactly 12.00 AMUs. We're going to set this equal to H, which is the magnetic field strength for those isotopes. And this is squared. So I'm going to make up some numbers here for the magnetic field strengths. But again, I want to determine the mass of neon 20. I know the mass of carbon-12 is exactly 12.00 AMUs because that is defined. Now these magnetic field strengths, I'm just making up the numbers, but you would get these from the mass spec. Magnetic field strength is measured in what's called Gauss. And remember to square that. So I would get this information here from the mass spec. I know the mass of carbon-12. That allows me to find the mass of the isotope neon 20 just by solving that. So the mass of neon 20 of just that particular isotope, and again, atoms are measured in atomic mass units because it's a really small unit of measurement. So 19.9924 atomic mass units. Now, if I know the abundances of each isotope and I know the masses of each isotope, I can calculate the atomic mass of neon because neon is a mixture of isotopes. So I want to determine the atomic mass, which is a weighted average of the naturally occurring isotopes. I have all the data that I need. There's 3 isotopes. What I'm going to do is take the abundance. I'm going to start off with neon 20, so I got abundance of 0.9092, multiply by its mass. And all of these numbers are determined from the mass spectrometer. And we're going to do that for each isotope. So then we're going to do neon 21. Abundance, change it into a decimal, 0.0026 is the abundance, multiplied by the mass from the mass spec. And it's up to you how many decimals you want to carry out here when you multiply. And then neon 22, its abundance, 0.0882, multiplied by its mass. Add them together. Now, the isotope that was in the biggest abundance was neon 20, so I would expect the atomic mass of neon to be closer to that of neon 20. When you add these together, you get an atomic mass, which is what you see on the periodic table, of 20.17 AMUs. So this is the weighted average of the naturally occurring isotopes, and that's what you will see on the periodic table. So the periodic table shows the atomic number. The atomic number is the number of protons. The number of protons identifies the element. So in this case, like 12 Mg, 12 is the atomic number. It identifies the element as magnesium. No other element has 12 protons. It tells you the chemical symbol and the atomic mass. And the atomic mass is always a decimal. And the atomic mass is the weighted average of the naturally occurring isotopes. Atoms are too small to count or weigh conveniently, so we need a unit that contains a specific number of particles for each substance and is large enough to weigh accurately. That unit we define as the mole. 1 mole is the amount of a substance that contains as many elementary units as there are atoms, and exactly 12 grams of the carbon-12 isotope. This number is Avogadro's number and has a value of 6.02 times 10 to the 23rd. Okay, so what does that number mean? 1 mole of the isotope carbon-12 contains 6.02 times 10 to the 23rd carbon-12 atoms and has a mass of 12.000 grams. Because carbon-12 is my reference isotope, the mass is exactly 12.00. 1 mole of the isotope oxygen-16 contains 6.02 times 10 to the 23rd oxygen-16 atoms and has a mass of 15.9948 grams. However, most elements are a mixture of 2 or more isotopes. And so the atoms that are to be counted out to yield 1 mole are not all of the same mass. So 1 mole of carbon, not a particular isotope, but just 1 mole of carbon, which contains all the isotopes of carbon, consists of 6.02 times 10 to the 23rd carbon atoms and has a mass of 12.011 grams. Now this number right here is the atomic mass for carbon, and that will be on the periodic table. 1 mole of oxygen consists of 6.02 10 to the 23rd oxygen atoms. That's a mixture of all the isotopes and has a mass of 15.999 grams. This number again is on the periodic table. That's the atomic mass of the isotopes of oxygen. So 6.02 times 10 to the 23rd atoms, which is 1 mole, is the number of atoms whose mass in grams is numerically equal to the atomic mass of the element in atomic mass units. Now the AMU and gram scales are dramatically different. I'm not going to go through the conversion here, but 1 AMU, that's how we measure individual atoms, is equal to 1.661 times 10 to the negative 24th grams. So AMU, that's how we measure individual atoms. but we can't measure AMUs in the lab, so we need a scale, and we're going to use the gram scale. But they are dramatically different scales. Just kind of keep that in mind. The mass of 1 mole of atoms of an element, which is called the molar mass, can be obtained from the periodic table. So for example, 1 mole of lithium is 6.941 grams of lithium. So that number is on the periodic table. Let's look at a couple problems. How many atoms are present in 5.2 moles of nickel? Start with what I'm given, 5.2 moles. I want the number of atoms. I'm going to cancel moles. Well, in 1 mole of any element, the number of atoms is the same, 6.02 times 10 to the 23rd. I know in this case we're looking at nickel, but any element has 6.02 times 10 to the 23rd atoms in 1 mole. So multiply those across, number of nickel atoms in 1 mole, 3.13 times 10 to the 24th nickel atoms. What is the mass of 4.82 moles of iron? Start there, 4.82 moles. If I want mass, I want grams. I can get the molar mass of iron from the periodic table. Anytime I'm looking at grams, look in the periodic table, get the molar mass. For iron, and I round to 1 decimal place, find its atomic mass, 55.8. Multiply across, that will give me the mass of 4.82 moles of iron. So grams, get molar mass from the periodic table. In this third example, how many atoms are in 0.5 grams of B, boron? So we have 0.5 grams. How many atoms? I have to go through my intermediate unit, which is the moles. Moles appear in all these problems. It's an intermediate unit. So in 1 mole, the number of grams of boron, go back to the periodic table because I see grams, and round to 1 decimal place, 10.8 grams. That will get rid of grams. Once I'm in moles, I'm looking for atoms, and since boron is an element, the number of atoms in a mole is 6.02, 10 to the 23rd. 0.5 divided by 10.8, and then multiply by the 6.02, 10 to the 23rd. So the number of atoms in 0.5 grams (2.79 times 10 to the 22nd boron atoms).